Assalamualaikum and hi everyone. In this video, we will demonstrate how to apply the cofactor expansion method in a real-life scenario. We will show step by step how this mathematical concept can be used to solve practical problems such as finding unknown forces in a suspension bridge design. Let's start with our group introduction. The first member is me. My name is Muhammad Shazrul bin Sharuddin. And the second member of our group is Muhammad Hussaini bin Muhammad Hussein. And the third group member is Adam Muhammad bin Yusman. So first, I will start with the definition of cofactor expansion. Cofactor expansion, also known as Laplace expansion, is a method for calculating the determinant of a square matrix. It involves selecting a row or column of the matrix and summing the products of each element in that row or column with its corresponding cofactor. The cofactor of an element is assigned minor, where the minor is the determinant of a submatrix formed by removing the row and column of the element. And for the step for cofactor expansion, the first step is choose a row or column. The second step is calculate minus by removing corresponding row or column. The third step is to compute cofactors using sign such as -1, I plus j. The fourth step is multiply each matrix element by its cofactor. And the fifth step is add the result to find the determinant. So next is our case study. The title for our case study is Designing a Suspension Bridge. An engineer is designing a suspension bridge. The forces acting on the cables, towers, and roadbed must be balanced for the bridge to remain stable. These forces can be modeled using a system of linear equations, which is then represented as a matrix. To determine if this system has a unique solution, the engineer needs to calculate the determinant of the coefficient matrix. For the problem statement, the engineer needs to determine whether the proposed suspension bridge design is structurally stable. This requires checking if the system of linear equations modeling the forces acting on the bridge has a unique solution. The challenge lies in accurately computing the determinant of the coefficient matrix to assess stability. If determinant is 0, the design may lead to instability, while if it non-zero, the design is stable. Therefore, verifying the determinant possibly through manual cofactor expansion is essential to ensure the bridge can be safely constructed.
Now I'll tell you the purpose of our study. So the purpose of the study is to apply mathematical concepts in a real-world engineering problem by using cofactor expansion as a manual method to calculate the determinant of a matrix. By using mathematical concepts that I mentioned before, we will determine whether the suspension bridge design is structurally stable by analyzing the determinant. Finally, we will demonstrate how mathematics supports safe and reliable engineering designs.
Alright, so to find the determinant, first and foremost, we write the system in matrix form A and B. Then, we find the determinant of A along the third column by using cofactor expansion. And we get 39 as our determinant of A. We found that the value is not equal to 0, means that the system of linear equation has a unique solution. We are not gonna stop here, so we will proceed to the next step, which is to find how much force that can be applied by using Cramer's rule to make sure that the suspension bridge is stable. So we move on to the next step. To find the horizontal force, we must find the determinant of it first. We are gonna substitute matrix B into the first column of matrix A and rename it into matrix of AX. Again, we use cofactor expansion to find the determinant of AX. Then we will get 742 as the answer. We are gonna use the same method as the step 2 until we get the determinant of AY negative 158. Again, apply the same method to find the determinant of AZ. Then we will get 1616 as the answer. To determine the forces required to ensure the bridge stability, we can use Cramer's rule. To find the horizontal force X, we divide the determinant of AX by the determinant of A. The result should be approximately 19.03 Newton. For simplicity, we round the value to 2 decimal places, giving us a horizontal force of 19.03 Newton. Following the same steps, we can calculate the vertical force Y and the cable force Z, which yield negative 4.05 Newton and 41.44 Newton respectively. Note that a negative value is possible as it indicates the direction in which the force is applied.
For result and discussion, from our discussion, it is shown that we can use the cofactor expansion method to find the unknown forces acting on different parts of a suspension bridge. This includes the horizontal force where we call it Sx, vertical force Sy, and the cable force Sc. Based on our solution that Muhammad Hussaini just presented before, we found that the horizontal force X is equal to 19.03 Newton. The vertical force is Y equal to negative 4.05 Newton, and the cable force is Z equal to 41.44 Newton. Therefore, this proves that the cofactor expansion method can be used to accurately calculate the unknown forces in bridges structures. Finally, for the conclusion, our study used the cofactor expansion method to solve a system of linear equations related to suspension bridge. The equations help us find the unknown forces acting on the bridges, such as horizontal force X, vertical force Y, and cable force Z. We found that the determinant was not zero, which means when the determinant was not zero, so the system has to be a unique solution. So based on the calculated forces, we get that horizontal force is X equal to 19.03 Newton, vertical force is Y equal to negative 4.05 Newton, and cable force is Z equal to 41.44 Newton. It shows that the bridge is stable and the design is correct based on the given condition and solution. The study proves that the cofactor expansion method is useful for finding unknown forces in engineering problems.